We have a LCR circuit in this problem where, see, normally the power will be lost with time, but here the power is being supplied such that the oscillations are maintained at a certain energy. So this power is given to us. So let's read the problem. Find the quality factor if in a circuit we have capacitance L and if the maintenance of undamped oscillations with the voltage amplitude being equal to Vm requires a power P. So if P power is supplied, the oscillations become undamped. So we need to find what is the quality factor of that. It's given that damping is sufficiently low, which means beta is small. So because we are dealing with power, let's start with energy. So let's find the equation of energy and how it varies with time. So that's E naught e raised to power minus 2 beta t. So we have done this problem in 4.109 and 4.110 also. But let's quickly find this result again and then we will do the solution. So we know for damped oscillation our equation is of this form. X can represent voltage or current or charge, it doesn't matter. Now solution of this equation is of the form x naught e raised to power minus beta t sine omega dash t by plus phi, where omega dash is root omega naught square minus beta square. This term represents the amplitude of this quantity. So similarly, energy of the damped oscillation, so total energy can be written in the form of half Ka square. A is amplitude of some quantity because all those quantities are proportional to each other. Current, charge, their amplitudes. So energy can be written as half Ka square. So amplitude will be of the form x naught e raised to power minus beta t. So when you put that and square it, it will be of this form. So coefficient of e raised to power minus 2 beta t, so that is the energy at t is equal to 0. So that's the maximum energy E naught. That's why we can write the energy of a damped oscillation in the form of E naught e raised to power minus 2 beta t. And there's no sign function here, so it continually decreases to 0. So now let's keep this in mind and attempt the problem. So E is E naught e raised to power minus 2 beta t. Now beta is small, which means e raised to power minus 2 beta t can be approximated to 1 minus 2 beta t, as e raised to power minus x is approximated to 1 minus x for small x. So we have E as a function of time, so if we differentiate that, we'll get power. So let's do that. So power will be d by dt is equal to minus 2 e naught into beta. Now they have given initially the voltage amplitude across capacitor, not initially, the voltage amplitude is Vm. So we know that means that the energy of these oscillations, maximum energy of these oscillations will be half CVm square. So E naught will be half CVm square. And beta for LCR circuit is R by 2L. Now we don't know R, so that's how we get quality factor into picture. So R is 1 by Q root L by C. So this equation is also only valid when beta is small. So that's why we are able to use this equation. So we do that to get rid of R and we'll get this. So on simplifying we get this. So now we need Q. So from this term and this term, we'll get the value of Q, that will be Vm square by 2p root C by L. All right.